All right, let's get started. Today, we're going to take a look at an idea you've probably accepted your whole life, something that seems, well, totally obvious. But what if I told you that our everyday experience of how things move is actually deeply misleading? I mean, think about it for a second. You push a book, it slides for a bit, and then it stops. A ball rolling on the grass slows down and comes to a rest. It really feels like the universe just wants everything to stop moving, right? That being at rest is the default. But is that really what's going on? Well, it turns out our intuition here is built on what you could call an everyday illusion. We're so used to seeing the world a certain way that we're completely missing the real physics hiding in plain sight. So, yeah, everything we see reinforces this one simple idea. If you want to keep something moving, you've got to keep pushing it. If you leave it alone, it's just going to stop. And for thousands of years, that's exactly what everyone believed. But this view is missing a massive piece of the puzzle. So to see what's really happening, we have to kind of peel back that illusion. And we can do that with a little thought experiment, one that was first imagined by the brilliant Galileo. Let's unmask the real cause. Okay, picture this. You slide a hockey puck across a rough carpet. It stops almost instantly, right? Now, what if you slide that same puck across a smooth, polished wooden floor? It goes way farther. But here's where it gets really interesting. What happens on an air hockey table? That little cushion of air gets rid of almost all the rubbing, and the puck just seems to glide forever. See the pattern? With each step, we're removing something that was slowing it down. And that leads to the really big question. If getting rid of this invisible resistance makes the puck go farther and farther, what would happen if we could remove that force completely? What is this invisible thing that's been slowing everything down our entire lives? You guessed it, that hidden cause is friction. It's not that things naturally want to stop, it's that there's this external force, friction, that's always there, always working against motion. If you could get rid of friction entirely, the story of how things move would be totally different. And this brings us right to a revolutionary idea, one that was put into its final form by Sir Isaac Newton. It's so important, it's literally his first law of motion. You probably know it as the law of inertia. Now that sounds a little formal, I know, but the key word in that whole sentence is remains. This law is all about things keeping their status quo. If an object is sitting still, it's going to keep sitting still. If it's moving, it's going to keep moving in a perfectly straight line at the exact same speed forever, unless some outside force, like friction or your hand, comes along and messes with it. And this tendency for an object to resist a change in its motion, that's what we call inertia. You can think of it as the laziness of matter. Everything just wants to keep doing whatever it's already doing. But that brings up a really important question and a super common point of confusion. How do we measure inertia? To really get a handle on inertia, we have to be super clear about two words that people use interchangeably all the time: mass and weight. In physics, they are completely different things. Honestly, this is one of the biggest hurdles for students, so let's make sure we nail this down. So, how do we measure inertia? The answer is mass. Mass is the official scientific measure of how much inertia an object has. The more mass something has, the harder it is to change what it's doing, whether that's getting it to start moving or trying to stop it once it's already going. It's why it's a lot harder to get a bus moving with a push than it is a bicycle. The bus has way more mass, which means way more inertia. And this chart really lays it out perfectly. Mass is just the amount of stuff, the amount of atoms in an object. It's measured in kilograms, and here's the crucial part. It's the same everywhere. Your mass is the same on Earth, on the moon, or floating in deep space. Weight, on the other hand, is just the force of gravity pulling on that mass. It changes depending on where you are. Your weight on the moon is only about 1/6 of your weight on Earth, because the moon's gravity is much weaker. So let's do a quick check. An astronaut has a mass of 80 kilograms right here on Earth, then she flies to the moon. What is her mass when she's standing on the moon? If you said 80 kilograms, you are absolutely right. The amount of stuff she's made of didn't change just because she went to the moon. She's still just as hard to push around. Now, her weight would be much, much less, but her mass, that intrinsic property, is constant. Now, this might just seem like a simple physics concept, but this shift from thinking about motion as something that dies out to something that persists was actually part of a huge change in how we as humans approach the world. For centuries, going back to the ancient Greeks like Aristotle, the approach was to explain things by their nature. You'd ask, why does a rock fall? And the answer was, because its nature is to seek the center of the Earth. But Galileo and Newton completely changed the question. They didn't ask why things have a nature to move. They asked, what is the cause of a change in motion? And that is a monumental shift. It's the move from just accepting things as the way they are to actively searching for cause and effect. It's really the bedrock of all modern science, trying to find the universal rules, the mechanisms like friction, that explain why things change. Okay, let's do one more quick check-in, just to make sure we've locked in that really important difference between mass and, say, volume or density. All right, here's a classic brain teaser for you. What has more mass? A kilogram of big, fluffy cotton balls or a kilogram of dense, heavy gold? It's a trick question, of course. They have the exact same mass. A kilogram is a kilogram. It doesn't matter what it's a kilogram of. Now, the cotton balls will take up a ton more space, but the actual amount of stuff is identical. So let's just quickly recap what we've learned. An object's motion doesn't change on its own. A force, like friction, has to act on it. That resistance to change is called inertia. We measure inertia with mass. And, most importantly, mass is not the same thing as weight. And this all leaves us with one final, huge question to ponder. If an object in motion wants to travel in a straight line forever, why don't the planets just fly off into space? They're moving in circles, in orbits. So what is the invisible external force that's constantly pulling on them, constantly changing their direction, and keeping them locked in orbit around the sun? Something to think about. Thanks for joining me today.